Hello everyone, my name is Tanxin and I'm presenting for our Group 15 project, Alzheimer's disease prediction. In the next few minutes, I will introduce our dataset, key pre-processing steps, and how we prepared the data for machine learning models. Our project has three main goals. First, to explore clinical and lifestyle factors associated with Alzheimer's disease. Second, to conduct exploratory data analysis and assess data quality. Third, to develop a stacking ensemble model that predicts whether a patient has Alzheimer's disease. This slide summarizes the dataset. We use 2,149 patient records with 35 original columns. After removing two non-required fields, we keep 32 predictors, 17 categorical, and 15 continuous variables. The response is binary, where 1 indicates Alzheimer's disease and 0 indicates no Alzheimer's disease. Alzheimer's disease is a progressive neurodegenerative disorder. So early diagnosis is crucial for treatment and care planning. Prior studies have applied logical regression, random forests, and deep learning to multi-dimensional health data and achieved promising results. Most of them, however, rely on a single model. Our work instead explores a stacking ensemble to potentially gain more stable and accurate predictions. Before modeling, we checked the class distribution. As shown on this slide, patients without Alzheimer's disease are more numerous than those with the disease, so the response variable is imbalanced. This can bias models towards the majority class. So class balance is something we must keep in mind when training and evaluating. Next, we examined which columns were useful. We removed the patient ID because it is only an identifier, and the doctor in charge because it has most no variation and is confidential. Dropping these two variables simplifies the dataset without losing meaningful predictive information. We then checked for missing values. In this dataset, 9 of the predictors and 9 of the responses are missing. Therefore, we didn't need to perform imputation or remove any rows, which keeps the pre-processing pipeline straightforward. For continuous variables, we inspected histograms. Most of the distributions look approximately normal and do not show strong skewness because they already look reasonable. We didn't apply additional transformations such as logarithms. The models handle them after standard internal scaling. We also use the box plots to detect outliers among continuous variables. These plots do not reveal extreme values that would dominate the learning process. As a result, we kept all observations and didn't visualize or stream the data. For categorical variables, we converted categories into numbers using one-hot encoding. This creates a set of binary columns for each level of each variable. One-hot encoding is a standard approach that allows both tree-based and linear models to learn from categorical information. On this slide, we examine the pairwise correlations between our predictors using a heat map. You can see that most all of diagonal values are close to zero, and we don't see any large red or blue blocks. This means there are no strongly correlated pairs of predictors. So collinearity is not a major issue in our dataset. Therefore, we keep all predictors for the modeling stage without needing to remove or combine any variables.
Hi everyone. Since Nancy have already covered about the exploratory data analysis, I will be covering about the models, how we have trained the models, how we have tune the models, and the rest of the details. So we spend our data as a 85% of train set and 15% as a test sets. We use the stratified random sampling for this splits because our data is really unbalanced, so that we can get a really balanced structure in the test and the train sets. Then for the resampling to get out the best hyperparameters from the training set, we use the tenfold cross validations so that we can get the robust performance out of the training set, and we can use that in the testing set for the same hyperparameters. For the models, we have choose three different models as the base models, and on top of that, we have used the meta learner. So this setting is called the ensemble techniques, where we use the three different models, and out of those three different models, we create a new training set, and then that new training set becomes input to the meta models, and then we give the final prediction. So these are the combination of the three base models, logistic regression being the linear models, and other two being the non-linear models. We have really tried to capture the linearity and the non-linearity in the models. So the axis boostings and the random forest both being the tree-based approach, whereas the logistic regressions is a simpler, more robust for the simpler tasks and the data. So this is the combinations of the three models, and then we use the meta learner on top of it to get that robust performance. So out of 10 trend fold cross validations, here we have the plot for the first fold. You can see that we have these curve for the hyperparameter settings and the like the average AUC, ROC, and then out of all the folds, we find out what are the best parameters across all the folds. So this is the tuning plot for all of the four models. I would say one model, but yeah, three base models and one the meta learner. So this is the tenfold results for all across all the models, the logistic regressions, meta, random forest, and XGBoost. This is for the AUC, and we can see that the performance is high across the meta learners in the third fold, and we can interpret this. And then we have this another plot, line plot, where we have this accuracy plot versus the number of the folds. We see that the logistic regressions being much simpler models, they do not perform that well compared to other models, while the meta learners performing the best. This is the training summary results as we have discussed earlier. We see that the across 10 cross-fold validations, the accuracy is most of the high amount of mean accuracy is with the meta, high recall and F1s um, is by the meta models, and the precisions and the AUC comes from the XGBoost model. But the performance across all of them, when we check that, the meta learners really excels out on all of it. So out of all these models, we have tried to find out what are the best parameter settings that can really excel well for the testing set. So these are the models, their hyperparameters, and the best value across all 10 cross-fold validations. Then using those settings, we have tested our test results using the best hyperparameter settings. This is the result for the meta learners. So the accuracy is quite high, the precision is quite high, recall is 0.96, F1 0.96, and AUC has 0.96, and the confusion matrix also looks very nice. So it performed really well across the meta learners, similar with the best models. The best model also have a good confusion matrix, and the AUC curve. The logistic regression performs a little bit less compared to the other model, but yeah, it's one of the simpler models, so it can make sense as well. Then we use the explainable AI to and in and a SAP analysis to understand what are the best predictors or the most influential predictor out of all of those predictors. And we found out that the functional assessments, MMSEs, ADLs, and the memory complaints. So these are the top predictors for determining the model output. We also use the explainable AI or the SAP analysis to understand where the meta learners is learning most out of from. So that comes from the XGBoost first, and then the random forest, and then the logistic regression. So most of the output results comes from the XGBoost or let's say influenced by the XGBoost. So to conclude our presentation, we see that the meta learners achieve the best overall performances and have a high amount of high accuracy, F1 scores, and have a comparative AUC. So we can say that the ensemble learning really consistently improve the generalizations across the models. It reduces the variance and achieves the most balanced precision recall trade-off. And on top of that, other base models that are tree based, they also performs really strong and have a strong predictive ability. But overall, ensemble methods is more robust and clinically reliable for the Alzheimer's disease prediction dataset. So yeah, that's all from our presentations. Thank you, everyone.